All right, good morning, everybody. Welcome back. Get started here. Hope you're able to stay dry. No, it's kind of crazy right now. Cool. So a few announcements. You have homework 6 due Wednesday, turn on Tuesday for bonus point, usual stuff. Lab 6 due Friday. And I have my office hours today at FSM 4 to 6 p.m. So I'm not sure exactly how I'm going to do this, but we'll try to stay dry. But hop on over FSM, I'll be there, and we'll figure out some way to chat. So, yeah, cool. So a few goals for this week. We have like 2 weeks to the midterm now. So this week's going to be a lot of what we started on Friday. We're going to be doing that sort of again and again, but in a bunch of different examples. And so today we're going to focus on comparing distributions, categorical distributions, where there's more than 2 categories. So we technically already did this on Friday, where we had 2 categories, like you had like purple plants and like white plants. And so now we're going to do this with like more than 2 categories. Like, how do you assess a model in that type of scenario? It's a little bit more complicated. And then we'll introduce some terminology around that entire process of model assessment. It's actually called hypothesis testing. So we'll put some terminology around that today. And then on Wednesday, we'll talk about what happens when you're trying to assess a model, but you can't just come to a conclusion by looking at a visualization. So on Friday, we had 2 examples where we like made this histogram of these simulated values, and then we saw like, where does the actual data lie relative to that simulation? And it was really obvious. Either it was like really far outside the histogram, or it was like right in the middle of the histogram, like in the Mendel case. And so on Wednesday, we'll talk about what happens when it's like kind of on the edge of the histogram and you're like not totally sure which model to go with. Like, should you go with the model or the alternative? So we'll talk about how we can do that on Wednesday. There's actually some nice clear-cut ways to make a decision there. And then we'll start getting into numerical data towards like the second half of Wednesday's lecture and all of Friday's lecture. So we've only done like model assessment for categorical data so far, but we'll get into numerical by the end of the week. Cool. So just a quick recap of the 2 viewpoints. We went over this slide at the end of the lecture on Friday, but it's just good to just do a little refresh here. And so in both of those examples, there were 2 viewpoints. You had the model, which is kind of like this well-defined chance model of how the world works. And then you had this alternative viewpoint, which was a little bit more generic. And so we'll look at each of the 2 ones. So for example, in the jury selection, the model was that the people in the jury panels were selected at random from the eligible population. And so this is a pretty well-defined model because we can actually simulate from this. We know what the eligible population is. In that case, it's 26% Black. And so we know that we could use something like sample proportions to simulate from such a population. And so that's our model. So it's like a well-defined way of how the world works probabilistically. And then the alternative viewpoint was a little bit more generic. It said, no, it's not actually sampled randomly from a population that's 26% Black. The sampling was actually biased against Black men. And so this is a much more generic statement. You can't really like simulate from this viewpoint necessarily, right? Because there's like so many different things that could mean, like maybe instead of 26%, it's like 10% Black, or it's 8%. Like there's all these different values that could be in that alternative viewpoint. So the alternative viewpoint sort of encapsulates like everything that can happen outside of the 26%, and specifically in the direction of the number being less than 26. So that's kind of what the viewpoint was there. And then for the genetics case, the model was that each plant has a 75% chance of being purple. So again, here, very explicit thing that we're saying. It's just like randomly sampling from a population that's 75% purple. And then the alternative viewpoint in that case was that, no, it's not 75%. It could be anything else. So in this case, it's even more generic than the jury selection, because we're not even saying a particular direction, like it's definitely more than or less than. We're just saying it's not 75. It could be 76. It could be 76.5. Like we don't know. It could be 5%. So all of those possible values are included in this alternative viewpoint in that case. And this is typically the setup we're going to see for these model assessments. So you always have like one model, which is like how we think the world works. There's like some chance model behind that. And there's like a specific way we could simulate from that model. And then you have this alternative viewpoint that is arguing against the model in usually a particular direction, or maybe might just say like any direction is fine. Like maybe it's more than or less than the value. So these were kind of like the viewpoints we had. And you'll see this set up again and again this week. And so the typical steps that we're going to follow to assess a model, and we did this on Friday already. The first is to choose a statistic that measures the discrepancy between the model, which is like what's theoretical, what should be happening, and then the actual data you observed. And so we talked about how a statistic is basically just a number to summarize your data. So the idea here is like, okay, I have some model of how the world's working, like maybe it's 75% chance this can be purple. And then I observe some data, I have my one sample that I get to observe. And I have to summarize the difference between what I observed and like what's happening in theory with a single number. And so sometimes that number could just be like the proportion that are within a particular category. Sometimes it could also be something more complex, like the absolute difference between the proportion and like what's being claimed in the model. So it varies depending on the context of the problem. And so we saw a couple examples of that. So in the case of jury selection, model was 26% Black in the population. That's what we're randomly sampling from. Alternative viewpoint was no, it's biased against Black men. And then the statistic we chose was the proportion of men that are Black within our actual sample of like 100 people. So that was a statistic. That was the single number we chose, proportion. In the Mendel's case, the alternative was that it's not equal to 75. And so in that case, low values are like evidence against the model and high values are evidence against the model. So we have like these two extremes that are both evidence against the model. And so to kind of combine those together, we said, let's just look at the distance from 75. So rather than looking at the actual proportion that's purple, let's take whatever the proportion is and then find the distance to 75. That's what we chose as a statistic. And then once you do that, then what you want to do is simulate a bunch of data, assuming that the model is true, and generate a statistic for each of those samples. So that's why we had that for loop. So like 10,000 times we said, simulate data from the model, same sample size as our actual data, calculate the statistic, and then do that same process like 10,000 times. And then once you've done that, you can compare your actual data that you observed to the predictions of the model, basically the simulations. And the way we do this is we draw a histogram of the simulated values, and then we basically calculate the observed statistic from our actual sample, and then see how far that is from the histogram. So we did that process 2 times on Friday, and we'll do that again today. But this is kind of like the general set of steps that we're going to follow whenever we have like some model of the world and we want to see whether it's actually true. So any questions about this process or the steps throughout the process? Okay, cool. So we'll see another example of this today. Sweet. So let's try to do a discussion question maybe to start. So you've seen a couple examples already of how to do some model assessment. And so let's look at a new example here. So in this case, what we're going to be doing is we have this coin and we're going to toss it 400 times. So that's going to be like our sample. And there's going to be 2 viewpoints of the world that we need to decide between. And these are 2 different questions, actually. So just for part A, imagine one viewpoint is the coin is fair. The other viewpoint is no, it's biased towards heads. And then in the second question, one viewpoint is the coin is fair. And then the second question, the alternative viewpoint is no, it's not. And so what you have to do basically is just come up with a statistic that will help you decide between the 2 viewpoints in each question. So you should have like one statistic for question A and then one statistic for question B based on this setup. So discuss with the person next to you and see if you can come up with like, what's that one number that you're going to use to summarize your data and that you're going to compare between the actual data and the model. All right, so let's try to see what you came up with. So I'll just make an example. Like, let's say in my particular sample, I just get to do this one time. So I happen to get like 250 heads out of 400 tosses. So let's say that's the data that I have. That's like the one data point I get. So what's the statistic you're going to choose to summarize that? For question A, let's say. Any thoughts? What'd you guys come up with? Yeah. Yeah, the proportion of heads that we got. So if we got 250, I would just do 250 divided by 400. That's going to be a proportion of heads that I got. Any other suggestions or ideas that came out besides the proportion of heads? Everyone got proportion of heads? Someone definitely got something different. Yeah. Yeah, so another one could be maybe the absolute difference between the proportion of heads and maybe like 50% or something. If you think this coin is fair, right? That's like what we would expect to see, 50%. So that could be another one. Yeah, another one you could also do is actually the number of heads that you got. So you could just do that as well. So I could just say, hey, I'm just gonna look at the number of heads. I got 250. Let me go do that with all my simulated values. And let's see what I get. If it's a fair coin, most of the time I'm gonna get around 200. Sometimes I'll be above, sometimes I'll be below. But I can make a histogram of that too. So you could actually use the number of heads, or you could use the proportion of heads. Both are actually fine in this case. The absolute value one actually in this case won't quite work because typically what we want to do is we want to choose our statistic so that it's going to be high values of our data are going to be like towards one viewpoint and low values are towards another viewpoint. So you kind of want to make sure that like you choose your statistics such that that happens. And so if you look at the two viewpoints here, the first viewpoint is the coin is fair. And then the other one is no, it's biased towards heads. And so what this means is if we get a really high proportion of heads, that's evidence for the alternative. If we get a low proportion of heads, that's evidence against the alternative. So basically for the model. And so the absolute value you mainly want to use if you get a situation where like both high values and low values are like evidence for the same viewpoint. If you ever get to that point, based on the viewpoints that you have, then you might need to use absolute values. In this case, we actually don't need to use absolute values. Just proportion is good on its own. So basically, if you just chose like, let's say the proportion that's heads, so we expect this to be around 50%. If it's biased towards heads, we would expect that maybe our data is showing us something much higher than 50%. And maybe my example of 250 out of 400 is very high. Like maybe that's a very high number, and that's unreasonable. Then you won't really know until you actually do the hypothesis test or you do the actual model assessment. But in general, that's kind of how you decide between the statistic. And then for the second case, where the model viewpoint is exactly the same, the coin is fair, so we should expect around 50%. But the alternative viewpoint is more generic here. So it's saying, no, it's not 50%, it could be anything. And so this is very similar to like Mendel's example. And so this is a situation where you'd want to actually use the absolute values. Because if you just, for example, if you just try to use like the proportion that's heads, what you're going to find is, let's say I have my histogram of values, and then I observe something that's very high in terms of proportion of heads, right? So that seems to like it's evidence against the model. It seems like it's not fair, right? But then look at the other extreme. If I observe something that's really, really low, like let's say I get like only 10% heads, that's also evidence against the model. And so I have a situation where like both high and low values are like evidence against the model. And so you want to try to avoid that in general for your like visualizations. You want to try to make it so you're just looking at one side or the other of the histogram. And so a way to kind of get around that is to use absolute value. So when you use absolute value, you basically take your graph and just like fold it on itself, essentially is what you're doing. And so in this case, you should try to use absolute difference between the proportion and 50%. That's what we should be using as our statistic. And that's what we're going to want to calculate for all of our simulations. So any questions on that, the difference between the two and like why we would use one statistic versus another in those situations? Does that make sense? It's pretty similar to what we did on Friday. Actually, it's almost exactly the same. Cool. All right, so yeah, this is just a suggestion. This is just a summary here. So basically for both A and B, percent of heads is a good starting point. You'd expect around 50% to be like evidence for fair. But what you'll find is in part A, large values suggest that it's biased. So you can just use the percentage of heads. In part B, both large and small values suggest that it's not fair. And so in that case, you want to use the absolute value, the difference between the percentages. And for both of these, you can actually just replace percentage with number. That's also fine. So you could just say number of heads, And then here you could say number of heads minus 200. In this case, you could do that as well. It's actually going to give you the exact same result. So you can go either way on this. But the main thing is just make sure you're consistent. Whatever statistic you choose for your data, make sure that's what you're also going to use when you're like doing your simulations. That's the main thing. All right. So let's go into our next example. This is going to be another jury selection case, actually based out here in Alameda County. And so we've kind of already gone over this process before, but you have your eligible jurors in a county. Then you have your list of eligible like residents. This is like one extra step actually that we're showing here in this case, because this is like for Alameda County. And then you have your jury panel. And then finally you have like your jury selection. It gets down to just the final jury. And so the California Code of Civil Procedure says something very similar to the US Constitution, but it's actually even more specific. So it says all persons selected for jury service shall be selected at random from a source or sources of inclusive, that's inclusive of a representative cross-section of the population. So basically it's like a random sample of kind of the eligible population here. And so let's take a look at the actual data set. So here's our demo. And so actually, let me zoom out a bit. So this is what we have in our actual table. And so we have different like ethnicity categories here, and then we have the proportion of the population that's eligible to be on the jury. So you have like 15% of the population is Asian and so on. And then what we have is the actual panels that came out. And so these are the actual panels that were done. And so this is kind of like empirical. This is like what ended up happening. This is the actual data. And so what we're having here is it's really similar to the other jury panel case where you have this like eligible population, but then you have the actual panel that came about, and you try to understand how different are these two. Is this unreasonable, or is this something that could happen by chance? Is it possible that we could get these kinds of numbers by chance if this was the actual population? And so we'll try to go about a very like similar exercise. And so one thing we can try to do maybe is instead of looking at these in a table, it might be nice to look at these in an actual chart. So what's a good chart we could use to compare these? Yeah, so we could try a bar chart because these are categorical. So we have like different categories. We have like the percentage that's in each category. So it seems like a bar chart could make sense. So we could do jury.bar H ethnicity. And so this shows us the same exact information, but now in like a visualization. And so we can see eligible is in blue and then panels are in gold. And so it's quite easy to see here like the differences between like what's eligible and what was actually selected. And so, you know, clearly seeing like some differences here on at least some of the categories. But the question is like, is this real? Is this something that could just happen by chance? I mean, there's like 5 different categories. It's kind of a lot. And, you know, depending on how many people we're sampling, maybe like you'd expect a lot of variability here. We don't quite know. And so again, as usual, what we're going to try to do to assess whether this is reasonable is we just have to find a way to simulate from our data. And so firstly, let's pull out what the model proportions will be. So that's going to be what's eligible. So we're going to set that to our model. So let's just say model equals that array. So this is kind of like the theoretical thing that should be happening, that we should be sampling from, because that's the eligible population. And then if you want to simulate from this, we can go ahead and I'll just assign it to simulated. So we'll do one simulation. So the way we do this is we'll do sample proportions. In this particular case, I forgot to mention the sample size was 1,423. And then all we do is pass in these proportions here. So just like we did on Friday, only difference really is that we have more than 2 things in the array here because we have more than 2 categories. But otherwise, it's exactly the same code. And then we can take a look at what we get here. And so this is one particular example. So we get around 16% for Asian, 18.6% for Black, and so on. And so you can see a little bit how this might compare to the actual eligible population. And we can run this like a few different times. So you can just see how these numbers are jumping around. And so, you know, these numbers jump around like quite a bit, but probably not more than like 10% of their value or so, maybe 20% of their value. But you can see they do move around a little bit. And so one thing that might be helpful is to, let's just take one of these simulations and add it to our table. So let's do jury with simulated, and then we'll just do jury with column. Let's just add a new column for the simulated value. So again, here we're just doing one simulation. So It's not going to tell us the whole story, but it's at least just an example of what's happening. And then we can put it all together here. And then of course, instead of just looking at a table, we might want to actually just visualize this. So we can do a bar chart on this new table. And then we'll do the exact same set of code, but on a different table. And so now you can kind of see visually like how different it really is. So we still have like the dark blue is eligible, the gold is panels, and then this light blue is like simulated. And so you can see the simulated is like pretty close to the eligible. And that should happen in general, like that's the point of the simulation. But the idea is we want to get a sense of the variability. Like, will we ever get a simulation where this bar gets like as low as this? Will we ever get a simulation where this bar is as high as like this gold bar? It could happen. We've only done it a few times, but we got to do it again and again to actually understand what's going on here. Cool. So one thing we have to do is that, you know, in order to actually assess like how different they are, right? We have to come up with that statistic. We have to summarize our data by one number. So if we go back to our data is basically what we observe is this column right here, panels. That's what was actually observed. That's like the one sample we get. And so we have to somehow summarize that column with a single number to kind of score like how close it is to the eligible population. So any guesses on how we could do that? Because we have like 5 numbers here. This was really easy on Friday because it was just like, okay, let's just look at the percent that's black, and then that's our number, that's our statistic. But we can't quite do that here because I have to compare like all these different categories. I can't just look at one number on its own. So any thoughts? How could we try to summarize this data that we have into like a single number? Any guesses? What's like one of the first things that maybe comes to mind when you're like thinking like, okay, I got to summarize this with a single number? Any thoughts? Yeah. Yeah, so we could do something like with the difference maybe between these two, right? Like that seems like a good start. So let's actually take a look at that. So actually, we can just do this with the original jury. So let's say we could do like the jury column panels. So that's what we actually observed. And then let's take a look at jury to column eligible. So if we do this, so we take one column, subtract another one, we get another array of 5 values. But we still got to get this down to one number. So what else can we do here? This feels good. Like this feels like it's in the right direction, right? We're getting a sense of like how different the observed is from the theoretical. But we still have 5 numbers, like 5 differences to deal with. Yeah. Yeah, maybe let's take the average of this, right? So we could take this thing, let's just call this like diffs, and then we could maybe take the average of this. Oh, sorry, let me show it to you too. So let's do like np.average diffs. Oops. Okay, so we get 5.55 times 10 to the minus 18. So what is this? What's going on here? Any idea? What does this mean? Yeah. Sorry, can you say it a little bit louder? What is this number? Any idea? What does this mean? It's like a really tiny number. It's like times 10 to the minus 18. Yeah. Yeah, it's near 0, right? So this is just like a little Python thing. We talked about this like in one of the first weeks, right? Like Python, especially with like floats, there's only so much it can represent. And so there's probably like some sort of mathematical error that's happening here. But essentially what Python is finding is like the result is like something really close to 0. In this case, it's actually exactly equal to 0. And you can actually just add these up yourself to like verify that too, right? But we have like, if you like add these up, then you'll see that it's going to be, it should like 0 out basically. Well, I guess there's like a little bit of rounding error, but yeah. And so that's actually what's happening here. And so why is that happening? Why are we getting a difference of 0? So what we basically did was we took this entire set of data, which is this column, we subtracted individually row by row all of these ones, And then when we like took the average of that, we got 0. So one hint there is that the average of, let's say, like a column of data, like let's say these 5 data points, in order to calculate that, the first step is you sum them up. So you sum up all your values and then divide by how many there are. And so there's 5 values on the bottom. So we know we're dividing by something reasonable. So probably the sum is equaling 0. So that's like a little bit weird. Let's see what happens if we do this with the simulated one as well. So let's just take simulated. Sorry, this should be jury with simulated. And then take the average of this. Let's see what we get. Or actually, let's just take the sum to see what happens. All right, so just summing that up, we also get something really weird. In this case, it's like negative 5.5, but it's times 10 to the minus 17. So it's like basically 0 again. So it seems like if we take a column and we subtract another column and then we just add up the values, it's like always equal to 0. It's like, that's a little bit weird. Any guesses on why that's happening? Why is it that like this entire column and this entire column, if I take the difference, it'd be 0? Yeah. Yeah, you have like negative and positive values, so they might cancel out, right? But why is it like canceling out to exactly 0? That seems a little bit strange. Any thoughts? It's like so perfect. Why is it happening? Yeah. Yeah, so each of these columns are proportions. This is a categorical distribution. And we talked about how this is like one of the most fundamental things in like probability is like the probability of everything has to add up to 1. And so what that means is if I have all my categories, if I go down this column, this whole thing needs to sum up to 1. That's just like that's the definition of like a categorical distribution. It needs to happen. 100% of everything needs to be represented in my table here. And that's going to be the case for all these. So whether it's my theoretical distribution, whether it's my observed one, whether it's a simulated one, it's always going to add up to 1. That entire column, it has to add up to 1. That's just how categorical distributions work. And so if I have something that adds up to 1, I have something else that adds up to 1, and I like subtract them and like sum it all up, I'm going to get something that's 0. Because basically I'm taking 1 minus 1, like at that point. And so that's what's happening. So, you know, it doesn't really matter how you try to do the math here. You're going to actually end up with 0 every time. So this is really close to what we want. It seems like we were in the right path here, but we got stuck because like the positive, the negatives are canceling each other out, like someone mentioned. So what's something we could do to get around that? How could we get around the positives and the negatives canceling each other out when we like add up all those numbers? Yeah. Yeah, so we could try to use absolute value, right? So maybe what we can do is let's actually, instead of taking the sum, let's do like the absolute value of the difference. And then let's take the sum after that. So actually, first of all, let's just do absolute value. And we'll just do absolute value of diffs actually. So you can see the original one. I'll move this up a little bit too, so you can see them next to each other. So if you do absolute value first, 0.11 stays as 0.11, negative 0.1 becomes positive, negative 0.04 becomes positive. So basically everything's positive now. And so now if I go ahead and take the sum, we should get a single number, and we do, it's 0.28. So that's kind of cool. And then we could do the same thing with the simulated. So we can take the difference of the simulated and the theoretical, take the absolute value of all the differences, and then sum that up. And in this case, we get a difference of 0.04. So in this case, we don't really know like what this value really means. Like, I don't know what 0.04 really means. I don't really know what like 0.28 means, but at least I have a number now. I have a statistic, a number that has summarized my data and that I can calculate for my simulated values. That I can also calculate for my observed values. And now I have a way to compare like which one is like farther away from theoretical. I have a way to calculate that now. So I basically come up with this like new number. But like hopefully intuitively it makes sense like why we're doing this. We were just looking at the difference in the distributions and we just wanted to make sure it doesn't cancel out. So make everything absolute value. And so it's going to turn out that this statistic has a name and it's used a lot throughout data science. And so just to recap a bit, so we have people on panels that are of multiple ethnicities. It's more than just 2. We know that the distribution of ethnicities is categorical. And so to see whether the distribution on our panel is actually close to what was eligible, we have to measure the distance between those distributions. And we know that they're categorical, so they're going to add up to 1 each. And so there's like something we have to do a little bit more. And so the solution is actually called total variation distance. So this is just a fancy name for what we just showed you, basically. But in this case, total variation distance, the way it works is for each category, compute the difference in proportions between the two distributions. So like take the percentage that was Asian in the panel, subtract the percentage that was Asian and eligible. Then do the same thing for each of the other ethnicities, go all the way down. Once you have that, you're going to have another array of differences. Then what you do is take the absolute value of each of the differences. We did that as well. And then finally, we're going to sum them up. And in this case, we actually divide the sum by 2. And so this particular metric or statistic, total variation distance, has this thing where you like divide it by 2. It actually isn't that important divided by 2. It's kind of the same thing whether you do it or not, but you just need to make sure you're doing the same math for your observed data as you're doing for your simulated data. But this particular statistic, we do divide by 2. So that's kind of what we're going to do here. And that's basically like the whole formula for this new statistic that we just learned. And so it turns out this is like a really nice, simple way to figure out the distance between two distributions. And then we can go ahead now and do the same thing that we just did for the observed data. We can go and do this for like a bunch of simulated data and see what kind of distances we get. And so let's go ahead and just like put this all together here. So first of all, let's make a function to calculate the total variation distance between any two arbitrary distributions, because we're going to need to do this again and again. So we can just call this TVD. And I'm going to have it have 2 arguments. So dist1, so the first distribution, and then dist2, the second distribution. And all we need to do is just follow the math that we had there on the slide. So first of all, we take the difference. So dist1 minus dist2. Then we take the absolute value of that difference. Then we sum up all the absolute differences. And then finally, we divide by 2. And now we have our function. And so we can go ahead and run this, for example, on jury.column panel, jury.column eligible. And so we can see what the actual total variation distance is for one single observed TVD. So I'm just going to assign this to something like this. And then we can take a look at what it has. Oh, no. Jury.column panel is not in the table. Panels. Okay. Sure, many of you have run into that in lab before. Cool. So I had the wrong name. Now we got it right. So in this case, our observed total variation distance is 0.14. This number is half of what we had before because we're dividing by 2 now. That's just like the way this particular statistic is defined. And so now we have a single observed statistic. All we have to do now is do what we did last lecture, which is like simulate a bunch of examples, calculate their statistic as well for each one, and then just see like what the histogram looks like. Yeah. Why do we divide by 2? Yeah, it's a little bit weird. It's like a little bit beyond the scope of the class, but I think a simple way to think about it is like you're taking an average of like the positive parts and the negative parts, like the positive differences and negative differences, and you're sort of like just scaling for the magnitude. But if you think about it, it actually doesn't matter. Like I could just remove the divided by 2, and like as long as I just have using the same function everywhere, it actually won't make a difference in the end results. But this is just kind of like classically the way that statistic is like defined. Yeah. Any other questions about the calculation here? All right, so let's actually finish the simulation here. So now we finally have a statistic that we can calculate. Now we just got to go through the simulation process, calculate it again and again. And so I'll make another function called simulated TVD, which will actually just do the whole process of like sampling from our population, calculating the TVD, and then returning that. So let's just do like all those steps in a single function. And so what we're going to do here is we're going to, first of all, do sample proportions, 1423, that's the sample size, sample from the model. So this gives us, actually, maybe I'll write this over a few lines. So we'll say simulated sample, and we'll just assign it like that. And then what we'll say is, okay, so we have our simulated sample. Now we're going to return the total variation distance between that simulated sample and the actual eligible population. And so if we do this, then we will have, actually, we can just write this as model everywhere here. So we'll have the distance between the model and the simulated. So it's the exact same code that we wrote here, except we're just replacing the panels, which is what we observed, with a simulated sample that we just created from the population. That's the only difference, really. And so this is what we're going to need to run again and again in a for loop. And so now we just have this all in a function. Again, we're doing this in a function, so we don't have to write like a bunch of code again and again. And then we can just now write our for loop. So we're going to just call this array TVDs. And so this is just like an empty array. And then we'll go through the process of doing our simulation in the for loop. So we'll do this 10,000 times like we always do. And then what we're going to do is we're going to generate a new TVD using this simulated TVD function. So it's nice and simple. And then we're just going to add it to our array. So TVDs equals np.append TVDs and the new one we just got. And so if you go back and look at like the code that we did for Friday, it was pretty much the same. You have an array of statistics that you're going to generate right now. And then in your for loop, every single time, you're going to generate a new statistic from a simulated data set. And so that's what this function does. And then just kind of make sure we store that. So go ahead and run this. And then the last step is to visualize everything. So I'm just going to write this out in a few lines because it's kind of long for some of these. So we're going to say the title of our plot is going to be simulated total variation distances if the model is true. If the model is true. And then for our bins, I'm just going to put some bins here. So I've kind of already looked ahead and I know what the bins need to be. So you don't need to worry too much about how we came up with these. In practice, you would kind of maybe do it without bins and then figure out what bins could make sense. And then we're just going to make a table, which is going to have a single column. It's just going to be the title here. And then the data set inside is going to be the actual TVDs. And then all we do is make a histogram with our bins. And so we can go ahead and do this. And this is what we see. So again, what is this the result of? We went ahead and simulated jury panels again and again from the eligible population, kind of assuming that's actually what's happening, randomly sampling from that. Then we did, what we did is we took that distribution from that simulated panel, compared it to the eligible, made a single number out of that, which is the TVD. And then we'd repeat that entire process like 10,000 times. So we have like all these TVDs, all these differences. And so this gives you a sense of like how your distribution might actually jump around. And so these are the different values that we see. So again, we don't really have a good sense of like what this value should be or what it really even means. But basically we know that the statistic, typically if you're simulating from the population, it's around 0.015. Sometimes it gets as high as 0.04. Sometimes it gets as low as 0, but it doesn't really go outside that range in general. And so the last thing to do is just compare this to what we actually observed. And so what we actually observed was 0.14. So that wouldn't even be like on this chart, essentially. So it's going to be like way, way out to the right. So essentially what that's saying is the distance that we observed in the actual panel from the population is much farther than what you would ever see if you like randomly sampled from the population again and again, 10,000 times in this case. So even if you do 10,000 simulations, you never see anything like as crazy as what we got in reality. And so this is another situation where our conclusion is basically that we have evidence against the model here. The alternative viewpoint is consistent with our data as opposed to the model, which in this case, alternative viewpoint is like there was some sort of bias. So any questions about that result, that conclusion? Cool. So it's pretty similar to what we did before, right? But the main difference is we're just using a different statistic here. So this data was a little bit more complicated. We had more categories, so we had to come up with like a different number to summarize our data. But that's pretty much the theme. Like you got to come up with a number to summarize your data, and then calculate that same number for your simulated data, and then just do that like 10,000 times. Those are like pretty much the sequence of steps. And then that number that you choose actually depends on the viewpoints that you have and what the alternative viewpoint is. Cool. So to just summarize everything, basically we wanted to assess whether we had this one sample, was it actually drawn randomly from some like known categorical distribution? We use TVD as a statistic because it allows us to measure the distance between the two. And so we said is, okay, so we have a way to do that. Let's sample at random from the population, compute the TVD of each random sample from the eligible, repeat that again and again, and then compare. And so what we showed you in that histogram is an empirical distribution of simulated TVDs. This is actually really important. So if we go back to this plot, ideally what I'd want to do, if I wanted to have like the best possible answer and like the most consistent results, is I'd want to figure out what's the actual theoretical probability distribution rather than the empirical distribution. Like what's the actual chance of getting a TVD of like 0.04 if I draw it random. There is actually like some actual number there. But that's really complicated to figure out because I have to think about all the different possible combinations of like all the different ways I could get that sort of TVD. It gets really complicated. And so that's why we don't even worry about trying to like calculate the exact probability. So we just go ahead and simulate. And so this is basically like a set of approximate probabilities. So if you go ahead and do this same set of code on your computer, your histogram might look slightly different. Like maybe this bar will be a little bit taller than this bar or something. So it might move around a little bit. It shouldn't look that different though, because we've done 10,000 simulations. But it might look a little bit different. And that's okay. We kind of accept that maybe there's a little bit of noise here. But in this case, it doesn't really matter. Like even if these bars are like a little bit different, the fact still remains that the 0.14 is like really, really far out. So that's not really going to change for any of us if we try this experiment. But it's important to remember that there's a little bit of variability in your results. And so we look at that empirical distribution, and then we compare that to the actual TVD from the sample in the study, see how far apart they are. And that's kind of how we make a decision. And so if the actual TVD was like right in the middle of the histogram, then we'd say, okay, actually the model is consistent with the real world. And then if it's really far away, we say it's not. And so this entire process is actually just called hypothesis testing. I used that terminology by accident earlier, but that's basically what this is called. This is what we've been doing. And so a hypothesis test in like general chooses between two views of how your data are generated. Both of those views are called hypotheses. So when we had the model and the alternative, those are just two different hypotheses of like how the world works essentially. And then the test, which is like the entire process we just did, the whole point of the test is to like pick the hypothesis that is better supported by the observed data. So we're not necessarily saying that the one that we pick is true. Like if we actually say, in like Mendel's case, we saw that the observed data was like right in the middle of the histogram there. And so our conclusion was that the data is consistent with the model, but we're not saying the model is true. Like maybe it's not actually 75%, maybe it's like 75.2%. Like we haven't really evaluated that yet. All we're really saying is like between these two viewpoints, this one is consistent with the data, this one's not consistent. That's all we're really saying. So we can't really make a stronger conclusion than that, at least at this point with what we have right now. And so that's okay, but that's still helpful to be able to do that. And just introducing a little bit more terminology. So when you have hypothesis testing, the two viewpoints are actually usually called the null and the alternative. So in our case, we were saying model and alternative. So model is the same as null. So usually the null is the one that you can actually simulate from. And so it's really important that you're able to simulate data under one of these hypotheses, at least one of them. And in our case, in this class, it's like usually going to be the null that we're simulating from. And so the null hypothesis is going to be a well-defined chance model about how the data is generated, which basically just means like we have a way to simulate from it using Python. And the alternative is just some different viewpoint about how the data is generated. And this could be a very generic statement. It can sometimes also be a specific statement. Like in Mendel's case, he was saying 75% purple. And an alternative viewpoint could be like, no, actually it's 70% purple. Like if you wanted, you could be that specific for an alternative. But in our case, it was very generic. It was just like, no, it's not 75. It's like literally anything else. So it just depends on the context of the problem and the setup of the problem. But that's just kind of like the typical setup here. And then one thing that we'll start saying a lot is like, we're simulating data under the null hypothesis. So what that means is we're basically saying, let's assume the null is true, and then let's simulate data from that. That's all we're saying there. And that's what we've done so far in today's lecture and Friday's lecture. So when we were simulating, let's actually go back to the code because this is good to point out. So when we went back here, right here, when we did sample proportions, notice how we passed in the model. So we didn't pass in the observed panel or anything like that. We passed in the eligible population very specifically because we want to simulate from the assumption that the model is true. That's what we're doing. And so that's really important. So this is always going to be like the model, like what's being claimed in the null. That's what you're going to simulate from. You shouldn't have anything about like your observed data inside your simulation function. And so that's all we mean under the null hypothesis. And then as we talked about, we have our test statistic. So we were calling it statistic so far, but in the context of hypothesis testing, it's called a test statistic. So it's kind of like that single number that you have to choose that allows you to like distinguish how far your data is compared to like the simulation. And so you're going to simulate the statistic, and then you're also going to calculate it for your observed data. And then a few things to keep in mind before you choose a statistic, because this is really up to you. Like you can make your statistic whatever you want. But you just have to think about what values of this thing are going to make us lean towards the null, what values are going to make us lean towards the alternative. Preferably the answer for the alternative in particular should be just high values. You don't want to be in a situation where you have like both high and low values. If you get into that case, that's where you might need to change your statistic and maybe introduce some like absolute values or something. And so that's like the general way to do it. I would say like avoid using absolute value. First of all, just think of like the simplest statistic, which is usually just like the proportion that's like in this category. Start with that, see what happens, just like play out some scenarios in your mind. Like what happens if my observed one is like really high? What happens if it's really low? If you start getting into issues, you might need to adjust the statistic a little bit. Maybe you need to subtract something else. Maybe you need to add an absolute value. Kind of go through that same exercise that we did when we arrived at the TVD in this lecture. And then, yeah, a little bit more just about like that simulation process. We call this like prediction under the null hypothesis. So basically what we're saying is that let's just assume the null is true. Like we don't know yet what's happening, but let's just assume the null is true. Let's simulate a bunch of data. Let's see what would happen if the null was true. And that's what we're doing in our simulation. And then finally at the end, we basically like compare those predictions or the simulations with the actual value. And really important, it's an empirical distribution of the statistic. That's why we're using simulation. We don't actually get the true probability distribution. Like we don't get to have the perfect answer there on like what exactly is likely to happen, but we're just approximating it. And that's like the main thing to remember, I guess, about this like prediction process, the simulation process. And that's okay because we're doing it like 10,000 times. So I just talked about like the law of large numbers. If we're doing that repetitions many, many times, our empirical distribution should look pretty close to the theoretical one. Not exactly the same, but close. And then finally, conclusion of the test, you just choose between null and alternative. How do we do this? You compare your observed statistic with the empirical distribution of what would happen if the null was true. And then if the observed value is not consistent, so it's like far from the histogram, then the test favors the alternative. If it's like inside, then that favors the model. And so typically a visualization will be enough, like what we've been doing. So in our case, we can just make a histogram and we know that 0.14 is like really far outside. We saw that on Friday as well. So like a lot of the times that's enough and you can make a conclusion. But we will see some situations on Wednesday where the observed value is like somewhere over here. So maybe it's like 0.035. So it's like kind of on the histogram, but it's like towards the edge. And so what do you do in that case? Like there's probably some point here where you're going to make a decision. Like maybe it's over here, it's the model, but then if it's like over here, it's the alternative. There's probably like some point where you're going to switch your decision. And so that's what we'll talk about on Wednesday, which is that if a visualization is not enough, we do have a way to make a decision still. And so that's what we'll talk about in the next lecture. All right, cool. We'll stop there.